In order to choose a good estimator, certain properties should be considered, one of them being that of unbiasedness. Since the estimator serves to approximate the value of a parameter, an unknown population characteristic, the value of the estimate should be, in some sense, close to the true value. For each sample collected from the population, we will obtain a different value of the estimator, that is, a different estimate. These possible estimates based on the sample selected do not necessarily coincide with the true value that is being investigated, which is normal since samples are a subset of the population that represents it. It would be desirable if these estimates were close to the true unknown population value, with some of these estimates being higher than the true value and others lower. The value around which the estimates lie is given by the average of the estimates. When this average value coincides with that of the population characteristic, the applied estimator is said to be unbiased. Its bias is null. Now, how can we calculate this average value? How do we compare it with the value of the unknown population characteristic? This is where statistics and, specifically, probability sampling come into play. The latter allow us to assign a probability to each selected sample and to each estimate calculated with the sample data. The average is a weighted mean value of these probabilities, and the probability calculus theory accounts for the rest. In a sample survey, estimators may initially be unbiased, but no response units not responding for the survey can lead to bias. If the non-respondent units behave differently from the responded ones, non-response bias will arise. To reduce this bias, calibration techniques are applied using auxiliary information available for all units in the population.